Good afternoon or good evening, and thank you for joining us today. My name is Allie Kane, and I will be the moderator for our presentation. I lead the implementation side of Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success. As with the other webinars, this will be a technical presentation intended for anyone who is interested in learning about Fluor's Cryo-Gas Deep Dewpoint process, or DDP. In case you're wondering, DDP is Fluor's award-winning technology for flexible natural gas liquids recovery for rich unconventional gases. Cost-effective, energy-efficient, and capable of achieving high product recoveries in 2 operating modes, DDP and its derivatives are a great fit for NGL recovery in the 2020s. We have 2 subject matter experts with us this morning. I'll first introduce Morgan Rodwell. Morgan is a Senior Director of Process Technology. He has over 25 years of experience in a wide range of industries and has worked in natural gas processing since 1992. Inside Fluor, he is recognized as a subject matter expert in process simulation. He has a Bachelor of Science degree in Chemical Engineering from the University of Calgary and is a registered professional engineer in Alberta and British Columbia. He lives with his family in Calgary, where he enjoys home renovations and cooking, but not baking because that's too much like chemistry. Joining Morgan is Bryant. Bryant Lynch is a senior process engineer from our Aliso Viejo office. He has over 8 years of industry experience with Fluor and the majority as an integral member of Fluor's gas processing technology team. He has had a hand in the design, implementation, and improvement of most technologies in Fluor's gas processing portfolio, including the deep Dewpoint process. Bryant has a Bachelor of Science degree in Chemical Engineering from UCLA, and he is a registered professional engineer in California. Bryant lives in Southern California with his wife and his puppy. He enjoys basketball, golf, water sports, and cars, especially the fast ones.
Thanks to everyone joining us. We really appreciate your time. It's an honor to be able to share DDP with you guys today. So I'd like to start today's presentation with a little bit of background and Fluor history. So DDP, as Allie mentioned, is one of Fluor's NGL recovery technologies that's part of a larger gas processing technology portfolio. So keeping that in mind, I thought I'd walk through some Fluor history in the NGL recovery field to start off. So as you can see from the items on the slide, Fluor has been involved in the gas processing industry for over 80 years and has developed technologies for NGL recovery throughout that period. So it started in 1939, Fluor was granted the first lean oil absorption patent for natural gas, which kind of got the NGL innovation ball rolling. From there, Fluor designed the first commercial natural gas turbo expander plant in San Antonio in 1964. So the picture on the left side of the slide is of that 150 million standard cubic feet a day facility. 2 years later, in 1966, Fluor was granted the first natural gas turbo expander patent. And then to top it off, Fluor designed the first reflux turbo expander plant at Judy Creek in 1974. So we've had quite a few firsts in the NGL recovery arena, but it hasn't stopped there. We're still very active in not only the engineering and construction aspect of NGL recovery, but the technological innovation aspect as well. We currently hold 23 active and pending patents related to NGL recovery technologies. So now that we're all Fluor history buffs, let's take a look at some of the market drivers behind the development of the deep Dewpoint process. So DDP was really born out of the U.S. shale gas boom that began in the late 2000s and continued into the following decade. So prior to the wide availability of these shale gases, the majority of conventional natural gas wells were producing a gas composition that was represented by the pie chart shown on the left side of the slide. These gases were primarily methane, often 85% or more methane, with little in the way of heavier hydrocarbons such as ethane, propane, butane, pentane plus. So looking at this from an NGL production perspective, these conventional gases would generally contain 2 to 4 U.S. gallons of NGL per every 1,000 standard cubic feet of raw gas that was processed. So kind of as a side note here, the acronym, you see the acronym GPM on this slide or other slides in the presentation, we're referring to this U.S. gallons per 1,000 cubic feet of raw gas rather than gallons per minute. So since these conventional wells were the most widely developed for such a long period of time, and these lean conventional gases were the most readily available, a lot of the NGL recovery technology development was centered around these types of gases. So contrasting these lean conventional gases are the rich shale gases, which are represented by the pie chart on the right. You can see that the NGL components, the ethane, propane, butane, et cetera, often make up over 25% of the raw gas. This results in an NGL content in the range of 5 to 12 GPM. Now, not all unconventional shale gases are high in NGLs. Some can be lean, some are high in carbon dioxide. However, the majority of shale gas deposits that are economically interesting are very rich in NGLs. So the driver behind Fluor's DDP was to tailor an NGL recovery process towards these rich shale gases. Okay, a few more points to hit on for the shale gases. As you can see from the map on the right side of the slide that was put together by the U.S. Energy Information Administration, these unconventional gas deposits are very large and distributed all over the world. However, in many places, these deposits are being developed in smaller plant capacities, often in the 100 to 300 million standard cubic feet a day range because of production methods or capital availability. Another big challenge facing these rich gas fields is that while propane needs to be removed, at least partially in order to meet pipeline Dewpoint specifications or maximum heating value specifications, the markets that drive propane and ethane recovery may happen on different timelines or even have some seasonal variability between the market timelines. So Fluor's development of DDP was cognizant of these challenges. In designing the DDP integrated solution, flexibility was paramount from both a process design perspective and an engineering and constructability perspective. So I've gone through the who and the what and the where, so on to the why. Why do we want to remove NGLs from raw natural gases? From an environmental perspective, decarbonizing natural gas has a positive impact on emissions when natural gas is burned as fuel. Ethane produces approximately 15% more carbon dioxide emissions per equivalent energy production compared to methane, and propane produces 22% more carbon dioxide compared to methane. The additional carbon mass that ethane, propane, and heavier hydrocarbons contain should also be removed before hydrogen is blended into the natural gas in order to reduce carbon dioxide intensity. From a transport perspective, as I mentioned before, natural gas distribution pipelines have hydrocarbon Dewpoint specifications. As the NGL content of natural gas increases, so does the hydrocarbon Dewpoint temperature. In pipelines located in colder climates, the ambient temperature could cool high Dewpoint gases below their hydrocarbon Dewpoint temperature, creating liquids in the pipeline, which is a transport no-no. As such, rich shale gases must be processed at a minimum to remove enough NGLs to meet these pipeline Dewpoint specifications. Then looking at it from an economic perspective, NGLs are valuable petrochemical feedstocks and products in their own right. Ethane, propane, butane, these are important feeds for plastics productions. Propane and butane can be used as standalone fuels, and pentane and heavier compounds can be blended into gasoline or used to produce solvents. So moving into the how. In order to recover NGLs from natural gas, it is necessary to cool the gas in order to liquefy the heavier molecules for separation. There are two basic routes. The first route is a closed-loop refrigeration system, which utilizes an external refrigerant, often propane. The energy required for the system is input via the refrigeration compressor, and cooling is obtained by Joule-Thompson expansion of the refrigerant across the valve shown in orange. So on the slide here, we've got the external refrigeration system shown in the green with the orange Joule-Thompson valves, and then the raw gas system shown in blue. So once the raw natural gas is cooled and NGLs are produced, the NGLs are separated out and the resulting gas is sold into distribution pipelines. Since the cooling of the natural gas is achieved by direct heat exchange with the external refrigerant, closed-loop refrigeration is limited to the normal boiling point of the selected refrigerant. So closed-loop refrigeration can handle richer gases because the ability to condense NGLs is limited only by how large a refrigeration compressor you are willing to buy. The richer the gas, the larger the refrigeration compressor required to liquefy the NGLs. In its simplest form, an open loop refrigeration system creates cooling by performing Joule-Thomson expansion of the raw gas itself. The JT expansion is again depicted by the orange valve. The energy input to obtain this cooling is provided to the compressor on the sales gas itself to recover the pressure loss during JT expansion. Open loop refrigeration can achieve lower temperatures because you're expanding natural gas from the high feed pressure down to the separation pressure, and the expansion of methane in the raw gas provides a large part of the cooling. So open loop refrigeration is very effective if the amount of liquids removed is relatively small. That's because you're using the resulting separated sales gas as a heat sink to cool the incoming gas. It's harder to recover the cold from the separated out NGLs because in doing so, you're reducing recovery. So all NGL recovery processes use one or both of these methods as a basis. If you look at flow sheets of NGL recovery processes over the last 60 years, you can see that there's novel developments, but fundamentally they're all one or both of these. The improvements in NGL recovery technologies over the years are attempts to optimize the capital and operating costs and come up with lower energy costs while achieving improved NGL recoveries. So the goal is to spend less to make more. On to turbo expanders. So turbo expanders were first developed to use in the air separation industry and then later applied to hydrocarbon processing. So as noted in the beginning of the presentation, Fluor installed the very first NGL recovery turbo expander. So the turbo expander replaces the Joule-Thomson valve. Expansion across a JT valve is isenthalpic. That is, the contained energy of the fluid on both sides of the valve is the same, whereas a turbo expander operates close to isentropic, often 80% or more, such that additional energy is extracted from the gas as it passes through the turbo expander. So this results in lower exhaust temperatures and improved recoveries while also providing useful power for sales gas recompression. However, the challenge with a turbo expander is that turndown performance is not very good. Like all rotating equipment, if the turbo expander operating point moves away from the equipment design point, efficiency is reduced. And as we've noted, in NGL recovery, efficiency is the name of the game. So for optimal results, turbo expander-based processing schemes have a relatively narrow operating range where turbo expander efficiency and stability are good. So the flow sheet on the slide shows a version of a turbo expander arrangement, a recycle split vapor variant that was obtained from a regulatory filing. Note that this flow sheet uses both open and closed loop refrigeration. This would have been necessary because there was insufficient cooling available from just the turbo expander pressure drop and the resulting quantity of residue gas remaining. Without, they needed additional energy input to get the temperatures required. The complexity of the flow sheet is tied to the goal of reducing energy consumption while achieving high recoveries and product purities. So a final piece of this flow sheet that is important to note is the use of residue gas recycle as reflux to the column. This is often a necessary feature to obtain very high ethane recoveries, but is expensive from an energy perspective on a marginal utility basis. As ethane recovery increases beyond 90%, capturing additional ethane requires relatively large increases in gas compression power as the recycle rate increases. The one last thing I want to touch on is the cost of propane recovery. The chart up on the slide shows a curve that compares the level of propane recovery on the x-axis versus the relative total installed costs on the y-axis for conventional NGL recovery technologies. On the left side of the curve are the low-cost, low-recovery options. These are the simple mechanical refrigeration units that use straightforward closed refrigeration loops, or the JT or dew-pointing units that utilize open refrigeration loops. Moving into higher recoveries but higher costs, we have refrigerated Joule-Thomson plants. These units combine both closed and open refrigeration loops to increase NGL recovery. And finally, on the right side of the curve, we have turbo expander-based processes. These processes result in the highest NGL recovery percentages, but have the highest relative cost. So as you can see from the chart, propane recovery levels beyond 90% have generally required turbo expanders. However, these turbo expander-based processes have been mostly developed for ethane recovery, where very low operating temperatures are required to grab that ethane, and high propane recovery is a natural byproduct. But what if there's a market for propane recovery but not ethane recovery? Fluor's driver with the deep Dewpoint process is to achieve high propane recovery but stay below the cost curve. With DDP, we've hit the sweet spot shown in the green box on the curve here, the propane recovery of a turbo expander plant, but at a cost more comparable to a refrigerated JT plant. With that, I'll pass it back to Morgan to go into a little more detail on the DDP process.
Thank you, Bryant. So, the Fluor Cryo-Gas Deep Dewpoint process, or DDP, is a combination of open and closed-loop refrigeration. It can achieve propane recoveries greater than 95% while rejecting more than 98% of the ethane. The C3 plus NL product contain low enough ethane levels that downstream fractionation may not require a deethanizer to meet commercial propane specifications. And while we claim greater than 95% recovery, we've achieved 98% in most plants, and if 99% is desired, it is possible, although the marginal cost to get there may not be economically attractive. Now to describe the process in more detail. The feed gas stream is split between a main cryogenic heat exchanger, designated here as a brazed aluminum heat exchanger, or BAHX, and a conventional propane chiller to provide the front cooling. This is done because for rich gas streams, the energy required to condense the NGLs is larger than the cooling available in the residue gas alone. A closed-loop refrigeration system is used to provide some of the cooling duty and to adjust the composite heat curve approach in the main cryogenic heat exchanger. This depiction shows a 6-pass cold box, but there are configurations with 4 to 7 passes. For large plants, it may be that the main core is broken into 2 units due to manufacturing limits. A propane refrigeration stream is shown going to the main cryogenic exchanger, and depending on the operating conditions and richness of the gas, this may or may not be required. The decision on this depends on the details of the composite heat curves and optimizing the design of this exchanger and the overall compression requirements. The gas is let down across joule thompson valve number 1, which provides the majority of the cooling. The cold exhaust stream provides the feed to the absorber column, which acts as both a mass and heat transfer device. Natural gas liquid-rich liquids exit the bottom of the absorber and are routed back through the main cryogenic exchanger to the stripper column as its top feed. A pump is required because in the DDP process, the stripper column operates at a higher pressure than the absorber. Separator liquids from upstream of the JT valve are likewise routed back through the main cryogenic exchanger and fed to the stripping column. The stripper overhead will contain a very high concentration of ethane, often in excess of 50%. This is recycled back and cooled against the absorber overhead. Liquefied, this ethane-rich stream is then flashed across joule thompson valve number 2. This provides a second open-loop refrigeration circuit and a high ethane reflux stream that helps capture additional propane. Other schemes on offer in the market do similar things, but utilize compressors, pumps, and other kit that makes the operation both more complex and less energy efficient. In the DDP propane recovery mode, the stripper column is reboiled using a heating medium, usually a hot oil. Now, the DDP process can be designed for feed gas pressures as low as 5,000 kPa, 725 ps, but 6,000 kPa or 870 psi or higher is preferred to avoid excessive refrigeration compressor sizes. The absorber and stripper pressures are adjustable, and optimization of these pressures, impacting the horsepower split between refrigeration and residue gas compression, is performed for the design. Normally, the operating pressure of the absorber will be between 1,900 and 3,000 kPa, 275 to 440 psi, and the stripper will operate a little bit higher. From our most recently built facility, we've proven out that the process is also quite resilient. The operating pressure of the absorber column can be adjusted significantly within the design capacities of the compressors and exchangers without any loss of recovery. In our configuration, a key design factor is that we make sure that the main cryogenic brazed aluminum exchanger has low thermal stresses, minimizing and avoiding discontinuities in the composite heat curves, and the approach over the full heat curve does not vary dramatically. This pinch optimization helps reduce the operating cost by using cold very efficiently. And finally, because this unit has no turbo expander, there are no concerns about turndown or falling off the performance curves or stable operating points. Turndown can easily reach 25%, and the operation is as easy as a simple mechanical refrigeration JT plant with much higher performance capabilities. The DDP configuration has some other advantages. the process is CO2 free resistant. Unlike some other cryogenic NGL recovery processes, there's no need to remove CO2 to low levels upstream of the DDP. Temperatures in the DDP absorber column and main cryogenic exchanger are maintained well away from CO2 freeze-out conditions for any gas that would meet normal pipeline specifications after the process. Next, with the two-column configuration, the columns are shorter than in a single-column plant, such as a GAP or RSV. For sites with more difficult road access, such as those in mountainous regions, this can be very beneficial. It further reduces the size or capacity of any crane required for construction. Now, this process is highly energy efficient and can be up to 10 to 15% lower horsepower than typical flexible schemes such as RSV, depending on the gas richness. Many of the historical technologies were originally conceived on leaner gas streams, as Bryant mentioned earlier. Fluor DDP was devised with rich gas in mind, and thus it provides a better fit to those feeds. The configuration is also simpler than some of the other high propane or flexible configurations. There's no recycles, no turbo expander, and no reflux drums or pumps or second mixed refrigerant loops. And finally, when compared to some other high propane recovery and ethane rejection processes, Fluor DDP is very easily connected to high C2 recoveries. This depicts the twin reflux absorption process extension to the DDP, or TRAP. This process is capable of achieving over 90% ethane recovery, and propane recoveries are over 99%. In the TRAP conversion, the only new components necessary are the turbo expander and booster compressor, and a single brazed aluminum heat exchanger that pre-cools the feed gas to the chiller by reboiling the stripping column, all shown here in red. The new brazed aluminum heat exchanger pre-cooler can use 1 or 2 reboil circuits from the stripping column, and depending on how rich the gas is, the hot oil reboiler on the column may fall to 0. A portion of the gas bypasses the turbo expander and is further chilled and then expanded across JT valve number 2 as reflux to the absorber. This provides the reflux to the absorber column, which increases the ethane recovery by being an ethane lean reflux in comparison to the DDP scheme's ethane rich reflux. The cold liquid streams from the separator and absorber are routed to the stripper. There may be scenarios, again depending on gas composition, where the cold separator liquids are still routed through the main cryogenic exchanger. The stripper overheads are routed to the absorber column to maximize ethane capture. The two columns operate at very similar pressures as compared to a difference of up to 50 psi or 700 or 350 kPa in the DDP mode. The operating pressure in trap mode will tend to be slightly lower than in DDP, but again, this is dependent on gas compositions. The main cryogenic exchanger is not changed out in trap mode. The same exchanger is used as in DDP mode. Some passes are repurposed. As it's configured, this is done with valving to switch over. And if a pass is not utilized in trap, it is simply isolated. We work with the brazed aluminum heat exchanger manufacturer in this regard to make sure that the design is effective in both modes. Another key aspect of the configuration is its tolerance to CO2 and avoiding freezing. It can handle CO2 contents up to 2 mol%, but this may result in a high CO2 content in the ethane product. Depending on the final market specifications, either upstream CO2 removal or treating of the NGL stream may be required. For example, in Texas, many NGL pipelines limit CO2 in NGL to about 1,000 ppm, while in Alberta, the end users generally have CO2 removal facilities and the pipeline spec is less stringent. When the design of the DDP process, at a minimum, we include all the connections for the trap model to be pre-installed. This makes adding CO2 recovery an easy revamp later. This includes layout configurations such that adding the new components happens adjacent to existing equipment without having to take anything apart except for the final connections. Alternatively, if your forecast ethane demand comes sooner, the design can include both modes from day one. Once the trap mode is installed, switching over can be done without a full shutdown. It can be performed while the plant is still cold and involves swinging a few valves and changing a few control set points. This can easily be done in a single shift. Finally, we do have a third, more extensive extension of DDP plus trap configuration, the enhanced residue gas recycle configuration, here shown in red, which utilizes a small recycle of residue gas to provide a second open loop refrigeration step via JT valve number 3 to reflux the absorber column with liquid methane. This can be used to push the ethane recoveries to very high levels. Again, functionality can be provided in the original design such that modes are easily obtainable without another revamp. However, like other recycle reflux schemes, this has a high horsepower cost for incremental ethane recovery. We do not see this configuration being as attractive as the DDP and trap configurations alone, but if ethane prices are high or decarbonization of the natural gas is a critical decision point, it may be a nice capability. Our first conversion of a DDP plant to enhanced residue gas recycle was completed in 2016 in Mexico. Now, our most recent DDP experience, we licensed our first small DDP plant in the United States in 2018. We worked with joule processing on this project and had 99% C3 recovery in DDP mode and 97% for the ethane recovery in trap mode. And this project was completed and we had a successful performance test in 2020. We had a few learnings on this project. First, during the performance tests, we realized just how flexible the process is. The operating pressure of the columns can be adjusted fairly significantly within the design capacity of the compressors to optimize performance while maintaining recovery. We also reinforced that Fluor, as a licensor, provides a lot of engineering guidance on a number of fronts that will help ensure good project outcomes once the plant is into operation. Our current business status is that we're working with partners in both the United States and Canada on packaged and modular offerings of cryo-gas DDP plants. The focus is on making these cost and schedule effective over a range of capacities. We're also currently proposing license designs for plants ranging from 100 to 800 standard cubic feet a day around the world. And finally, we actively look at revamp and modernizations of existing plants to improve their performance and increase flexibility. Now, before we go on to the Q&A, I just wanted to make mention of the memory of one of our great technology leaders, John Mack, who was one of our senior fellows in gas processing and NGL recovery, who unfortunately passed away in 2019, and it was a surprise to everyone. John had spent 46 years with Fluor and had published many papers and had been granted 49 patents over his career, and in fact was the most patented inventor at Fluor. He was also the author, or one of the co-authors of the Handbook of Natural Gas Transmission and Processing. So I just wanted to make mention of that we miss John a lot, but we're happy for everything he taught us over the years.
Thank you for that memorial, Morgan. And thank you, Morgan and Bryant, for your presentations. So I'm going to take a minute here now that we're at the conclusion of the presentation and see what questions we have that have come in. All right. So the first question, in the DDP configuration specifically, not trap, can a turbo expander be added in place of the main JT valve in order to save on closed loop refrigeration power consumption? And are there any operational concerns in doing so?
Yes, you can. I mean, if you had the turbo expander installed, you can operate it instead of using the JT valve. And if you were to design the plant that way from the very beginning, it could reduce the size of the refrigeration compressor a little bit. The operational concern again becomes the question of turn down, because as you start to, if the plant's to turn down, you may fall off the performance curve of the turbo expander. You can always at that point switch over back to the JT valve at a certain point, and we have looked at configurations where you could do that. And in fact, in the plants where we've designed it with both modes installed from the very beginning, often it makes sense to operate with the turbo expander at full load in the DDP's configuration.
Great, thanks, Morgan. Hopefully that answers our question from the audience member. Here's another one. What is the maximum C1 content that the DDP process is recommended for?
That one, it can vary because it also depends on the rest of the gas as well. It kind of, depending on what level C2, C3s the recovery targets. I wouldn't say that we can quote a solid number as the maximum C1 content.
I think that with regard to maximum C1 content, yeah, I don't think it's you can quote a specific number. depend on a number of other factors, including what's your inlet pressure and how much pressure do you have to run it across. We have looked at designs to use DDP even on relatively lean gases, and it works. The question of whether it's the best solution, it comes up to be needs to be evaluated.
All right, thank you. Next question. Do you have any recommendations for the amount of liquids acceptable in the inlet and outlet of the turbo expander?
Really, you shouldn't have any liquids into the turbo expander. That's why you place a separator ahead of the turbo expander. On the outlet of the turbo expander, most cases, we don't end up in a position of having too much liquid at the back end of the turbo expander. There are considerations depending on pressure more than composition about the actual fluid density into the turbo expander and what the phase behavior is, especially if you're near a supercritical region. But it's pretty flexible in that regard.
Thank you. All right, another one here. Can you elaborate on the ability to reduce residue compression based on efficiencies in the DDP?
Yeah, I think one of the things about the DDP and ways that we reduce the residue gas compression is really tied to what's the operating pressure of the absorber column. And if an operator at higher absorber column pressures, then we can reduce the residue gas compression requirements.
Right. All right, another one. I think I'm going to direct this one to Bryant. What are the factors affecting shale gas deposits that lead to the need for smaller plant sizes and flexibility in operation?
Sure. Yeah. So the map by the EIA showed that the shale gas deposits are all over the world. But as I had mentioned, that a lot of times they're developed in smaller plant capacities. And one of the things that's a little different, and it could be a little different between these shale gas deposits and conventional lean gas deposits, is you had conventional lean gas deposits where you could drill a number of wells into a deposit, and those wells would produce for 30 plus years, and you'd have a steady flow of raw gas for processing. Whereas what we see in a lot of these shale gas deposits is you drill multiple wells, and the wells have a lot shorter life, so that in order to continue the raw gas flow, that requires spending more capital on drilling more wells. And at some point, the drilling may need to occur further away from the plant itself, increasing transport costs. So there's a lot more variability in that regard. So it lends itself to less capital investment up front and then possible further development down the line.
Thanks for that, Bryant. Right, next question. Morgan, does Fluor help in the selection between the DDP, trap, or enhanced versions of the technology?
Absolutely. We will help in evaluating what the best fit is to a customer's business need. And we'll even tell you if maybe our technology isn't the best fit, to your specific needs. So, we're going to be honest with you about that, but we do fairly rapid evaluations of what the best fit will be.
Fantastic. All right, you mentioned that the design is highly flexible. What are the main adjusted control parameters in an operating plant?
I'll take that one, Bryant. The biggest control parameters will be the operating pressures of the two columns and the temperature of the cold separator. Are the primary control parameters that you would use to adjust the flexibility and manage what the compressor horsepower split would be.
Thank you. Another one coming in here. What are the general operating pressure ranges for the absorber and stripper for the DDP process?
Okay, to repeat that, the absorber generally will run between 1900 and 3000 kPa, or 275 and 440 psi. And then the stripper column would run about 350 kPa higher than that, or 50 pounds. It can be a little more depending on exactly what the gas richness is, but that's about where those operating pressures will be.
Great. Next question. Why is it preferred to remove NGLs before blending hydrogen into natural gas?
So hydrogen has a negative Joule-Thomson coefficient, where if you're expanding hydrogen across a Joule-Thomson valve rather than cooling the stream, it gets warmer. So it's actually counteracting the goal of dropping pressure to reduce temperature. So for NGL recovery and gas processing, if you are going to add hydrogen to a natural gas stream, you want to remove the NGLs first and then add the hydrogen to the resulting sales gas.
If I can just add something to that, Bryant, the other factor is that hydrogen is a really good stripping agent. So it reduces the partial pressures in the column for all the other components and tends to draw them out of the liquid that you've recovered. So, we've looked at cases where somebody wants to put hydrogen into natural gas and then run it through an NGL recovery process, and it has pretty dramatically deleterious effects on NGL recovery.
Okay, thank you. Now, Morgan, does Fluor's DDP design use trade or packed columns?
That's a good question. Usually at the smaller capacities, we would use trade columns in both columns. We have looked at, particularly for larger capacities, using a packed column for the absorber. The challenge with a packed column is that its turn down performance tends not to be as good if you need to run at a turn down case.
Okay, we have another one coming in. Does the DDP perform more efficiently in heavier inlet gas compositions or in leaner? Can you elaborate on this?
Because it was specifically designed around richer gases, its performance is better for richer gases, and its competitive position, its performance compared to other traditional routes is better on richer gases than leaner gases.
Okay, thank you. Next one, could you give us a general sense of the turn down limits for DDP, and what is it that limits the turn down?
Like I mentioned, or you want to take that?
I can take, yeah, sure. Yeah, so since there's no rotating, we have the pumps in the system, but those turn downs can be managed with, minimum flow recycles or similar. Since we don't have a turbo expander, as we mentioned and Morgan mentioned, the turn down is often 25% or better, and it's really limited mainly to tray efficiency in your columns at that point. So if you can go beyond 25% and your trays are still operating efficiently, that's kind of your limiting factor.
Fantastic. Well, I think that answers all the questions that we've had come in. So at this point, I think I want to just say thank you, Morgan and Bryant, for all the time you spent putting in to the presentation today. And thank you to our audience for attending. You've been great, and it's been a pleasure being your moderator today. We'll be hosting our next webinar on Thursday, February 11th at 9 a.m. Central, where Fluor Senior Fellow Peter Paul Pruin will talk about the digital twin. So keep in touch with your Fluor contacts. You can follow our social media postings or head over to the Innovation Builders page on fluor.com to register for this or other future webinars. So thanks again for attending today. We will send out a compiled list of Q&As within a few days, along with a notification that the webinar recording is available for replay on fluor.com. If you have any questions, more questions from Morgan and Bryant, perhaps, or you want more information, please feel free to email us at innovation.builders@fluor.com, and someone from our team will get back to you. And from all of us on the Innovation Builders team, we hope you have a safe day. And thanks again for attending.